you probably understand that we're still talking about ln, right? We're still talking about natural log. Important for you to know, we are not talking about the integral of natural log. We are talking about integrals that lead to natural log, right? That makes sense? Okay. If you take a look at an example like number 4 or number 5, I would say that these would be firmly in kind of that standard category like you saw in the video. So here's a chance to practice, if you guys would. Take a look at number 4. Let's just try this one together here at the start. See how this goes. I'll show you both methods. I think you can do Timmy messed up the chain rule with this. You can definitely do U substitution with this as well. So take your pick. Do what you think is best. I'll show you both ways here in just a minute. Work together. Check your answers. Here to help if you need help.
Better.
I didn't say anything about better or worse. I just made a comment. That's all.
They're kind of smart.
He's determined.
Then I can see like
in
my
other ways
progression,
that I'm
how it's bad, and then I learned like what
I should have wrote my answers just in my notebook and then printed off the notes for the test.
Shh. Listen up.
But wouldn't you just put the I don't know.
I'm listening. I mean, are you stuck or you're stuck? Okay. Ben, you want to share?
Well, I know you take like the derivative of the denominator.
Okay.
It's gotta equal the numerator, so I got 3. Well, 3 doesn't equal 1, so then
So in other words, Timmy
messed up.
messed up.
And so then we would have to multiply it by 3. Then you take the 1/3 outside of the integral.
Okay, let's stop right there. That's right. That's really good. If we're going to use the pattern, that's what we do. So the reason why he multiplied by 3 is because he determined the denominator's derivative is 3. And in order for this to be ln, then the top has to be that. And it wasn't, but it was fixable. Does that make sense? Bianca?
Yes.
Okay. So what Ben has constructed essentially here, he's constructed a perfect chain rule for leading to natural log. So once you've done this, we can really go right to the answer. Lainey, do you have it?
Yeah.
What do you got?
I got 1/3 log natural of the absolute value of 3x plus 2 plus c.
And don't forget the plus c. Yep. That's exactly right. That's exactly right. So you're going to be able to tell pretty easily, I really am a big supporter of using the chain rule pattern. Timmy messed up the chain rule pattern with these types of questions, simply because you can see it's basically kind of a 2-step process. Fix the numerator, answer. Right, that's basically it. Anybody want to see U substitution? I'd be happy to show that to you here. I can't say that in a normal setting I would do it that way, but I'd be happy to show that to you if you want to see it done. No? Any questions at all? Okay. I'll get you started with number 6. It does give you the hint to use a trig identity. Anybody have an idea about which trig identity we could use to get this into a form that would be helpful for us?
Sine over cosine.
Sine over cosine, yes. So if we rewrote this as integral of sine of x over cosine of x dx. Hey, why on earth would this be in the ln section of the notes?
The trick question.
It's not a trick question, although that could be it. Yeah, Hannah.
No, wait, no.
Okay. Why would this be in here? Like, why is this ln?
Because when you do it, there's going to be a natural log.
It's going to be natural log because it's a fraction now, right? It's a fraction, and the derivative of the bottom is related to the top somehow, isn't it? And so it's not a coincidence that this is in there. So please try number 6, the numerator.
No.
But it's close, isn't it? Timmy messed up a little bit by -1. So did you fix it? So Eliza identified the issue and she fixed it by multiplying by a -1. And then you probably had to adjust for that as well? That's right. So multiply the outside by a negative, multiply the inside by a negative. So Eliza has not done anything to change the value of it, but she has changed the form to a better form, one we can work with. Okay, so Eliza, why don't you finish it out? What'd you get? Shh. Guys, quiet down. Plus C. That's great. Right on the money. Questions? Concerns? Just a reminder for you on all of these. If you did one of these and you think, oh yeah, I think I got it right, but I'm not sure, how could you check? Go back and do a derivative. Yeah, do the derivative of your answer. You should end up with the original integrand exactly. So, okay. As I've been walking around, some of you guys have been working ahead a little bit, which is great. But I've noticed that most of you got kind of stumped on 7. And you know what? That's actually good because the normal methods that we've been using not going to work here. So if you're like, oh yeah, I did number 7, all this stuff's been working great, I'd be like, oh, I don't know if you're getting it. The fact that you got a little bit stuck on 7 is a positive thing, right? We want to get you past it, but it's a good thing that you had to stop and think. So let me help you out with number 7. Number 7 is obviously a fraction. And if I could kind of get into your thoughts a little bit, maybe you're taking a quiz or a test. Listen really carefully. You're taking a quiz or a test. You clearly identify this as a fraction. You think to yourself, hey, maybe it's ln. But then you look a little closer and you ask yourself, what's the derivative of the bottom? And you would say 1. And you're like, all right, what's the top? Definitely not 1, right? Like very different from 1. And in fact, you might even be tempted to say, man, I think Timmy has messed up so bad, it's unfixable. And I would say in this current form, yeah, unfixable. Totally unfixable. So, I can do it. I know I can fix it. Hey, listen up. I'm going to get you started on this. Here's the other characteristic I want you to notice. If you run into a situation like that where you're like, wow, the derivative of the bottom is like something real simple like 1. You look at the top and it's this big old polynomial and you're like, whoa, this is not working at all. Here's what you do. In this scenario, or okay, all right. Hey guys, I know you're really excited to do long division, but I think in cases like this, synthetic division is better. I really want to make sure you understand, like, did you guys in your pre-calc class, did you all do long division, synthetic division? Yes. Did you all do synthetic division? I think you did. Okay. Hey guys, again, I know you'd rather do synthetic. I would rather do synthetic as well, but I want you to understand something really important here, and I'm not going to try to mess around with you on this. If your denominator is 1x, plus or minus, like 2 or 5 or 7 or whatever, you can do synthetic division. But if your denominator happened to be like 5x minus 4, can't. Doesn't work. And so be aware of that. I think in just about all the cases we're going to see, synthetic division will be something you can do. But if it was 5x minus 4 for a divisor, then you're going to have to use long division. But in this case here, I'm definitely going to choose synthetic. Where are you guys at with this? Are you do you remember synthetic well enough where you could just take off, or you need some? I'm seeing a couple folks that are like, yeah, I need some help. Let me show you. If you think you can do it on your own, just go ahead. It'll be positive 2. Yep. You mean like a zero remainder? We could, but I don't think we will on this one. Yep. Hey, for those that are working, try to work quietly. I want to try to give some instruction for folks that need some help. Here's how you do synthetic division. You look at your divisor, and in this case your divisor is x minus 2. So here's what you do. You take the opposite of the number. So in this case it's minus 2, so we're going to write it down as positive 2, and I'm going to put it in this little box. The 2 goes like in this little half box. And then off to the right, what you're going to put is the coefficients of the dividend. So it's 1x cubed, so I'll put a 1, minus 4x squared, so I'll put minus 4, plus 7x, so you put plus 7, and then minus 10, so you put negative 10. You're just putting the coefficients out there. We're not putting the x's there. One little trick to this you want to be super careful of, I think in your extra practice questions there's one of these. You need to have all of the degrees represented. So did you notice that the degrees on the numerator go 3, 2, 1, 0? If the degrees went 3, 2, 0, you need to insert a placeholder, like a 0 placeholder. Maybe you remember that from synthetic division before. Yeah. It's not the case here. Like I said, I think your extra practice has one like that. Leave some space and draw a line. And here's how synthetic division works. Step 1, you just bring down that first one. Just bring it down, whatever it is. And here's the process. You take your divisor, which is 2, and you multiply it times 1. 2 times 1 is obviously 2. You write the result of that right there. Once you have written that 2 where it belongs, you take the negative 4 and the 2 and you add them. Negative 4 plus 2 is minus 2. And guys, once you've completed that cycle, it's basically, the rest of it is basically a repeat of that cycle. So you're going to take your divisor, which is 2, times that negative 2. And the answer, of course, is negative 4. And like before, you added vertically. So we're going to add vertically again. Positive 7 plus negative 4 is 3. And then the last step, or the last multiplication on this one would be positive 2 times 3 gives us 6. Just like we did before, you add vertically, and negative 10 plus 6 is negative 4. That make sense? So if you forget how to do this, this is at like minute 11 in the video. And go back and watch that process again if you want. Or any one of probably 10,000 videos on the internet of how to do synthetic division. But you want to be able to do that for sure. So what we do now is we reconstitute the integrand. And we use the 1, negative 2, 3, and negative 4 to do that. So the 1 becomes x squared. We're basically going to lose a degree because we divided a cubic by a linear expression. So instead of leading with x cubed, we lead with x squared. So it'd be x squared minus 2x plus 3. Notice the degree goes 2, 1, 0, just like the original degree went 3, 2, 1, 0. Now what do we do with that minus 4? Close. It's over the divisor, yeah. So it'd be minus 4 over x minus 2 dx. So we just take the remainder, we put it over the divisor as our final term. And maybe you can see now where this is going from that last term, why this would be in the natural log section. So here we go. We're going to go term by term. What is the antiderivative of x squared? 1/3 x cubed. What is the antiderivative of minus 2x? Minus x squared. Antiderivative of 3 is 3x. And then finally that last term is going to involve what? Natural log. Yep. So that 4 is just a constant multiple. I would pull it out and just think of this as minus 4 natural log absolute value x minus 2 plus c. I got it in. Oh, sorry, it kind of went off the edge. There's a plus c there, I promise. Question?
If we kept the minus 4 in and then counted it as if like in a second chain rule and multiplied it by like a 1,
You could.
would that be okay?
Yep, you could. So Catherine asked about this. This is valid. So if you had something like this, you could say, okay, the derivative of the denominator is 1.
Right.
The numerator is a 4, so Timmy's off by a factor of 1/4. So you could go times 1/4. But if you multiply the inside by 1/4, you got to multiply the outside by 4. And you'd get the same answer. Yep. I tend to pull out the constant multiples, but that works. Yep. Okay. I'm glad I could help you guys on that one. Do you guys have any questions? Who knew synthetic division would come back around and show its beautiful face, right? Long division, we're going to try to leave that one in the corner somewhere. Synthetic division, I'm okay with that. All right. I think we got one last one to talk about. And, yep, it's number 8. Says, find the area of the region bounded by that graph, the x-axis, and the line x equals 3. If you wanted to use your calculator real quick just to get a sense of what this graph looks like, welcome to do that. You don't have to. If you understand the concept behind this, you definitely don't have to. But if you want to get a look at it, that's fine. We'll try to set this up here together. I think those of you that graph this, does this not look like a hill? The graph of this? Like a nice round hill?
Assuming we start measuring at 0, y-axis is 0, so 0 to 3.
Well, maybe I'm off on that. Oh, you know what? It doesn't look like a hill.
Yeah.
Because it goes below, it must look like kind of a, yeah, because it goes below the x-axis on the left, doesn't it?
Mm-hmm.
Yeah, okay. So Let me think about that question real quick. Area of the region bounded by that graph, the x-axis. Well, not really. So check this out. Here's the graph.
So it starts where?
Doesn't the graph do that essentially? Okay, so if it's bounded by that graph, the x-axis and the line x equals 3, so the line x equals 3 is vertical line over there. There's really only one region, isn't there? If it's bounded by those things. Because I believe that in spite of my slightly off graph, I think it goes through the origin, right? The red one.
Yeah.
So I think
If you didn't do that, you just solved for a zero.
I think the graph would be helpful here, yeah. So you know what, a word about that, because some of you, I can understand why some of you might be like, oh my gosh, I'm a little nervous right now. Please don't feel like you need to be able to graph stuff like this by hand. If we were doing some quiz or test and I wanted you to do this exact question, I'd either make the calculator active or I would give you a graph so you could see it. Please don't feel like graphing some rational function like this in the middle of a calculus quiz is going to be a thing that I would do. I wouldn't. I don't want to make that the reason why you didn't get it. Okay. So we're talking about this region right here. So why don't I give you guys just a minute here to try to set this up. We're tying this back into chapter 4, obviously. Let me give you that moment here to try to set this up, and then we'll talk about results and answers and stuff. That we're talking about this area over here, and we're going to accumulate from left to right, and that area starts at the origin essentially, and it ends at the vertical line 3. So we're going to accumulate across that region, but I think it's really important for us to talk about what it is we're actually accumulating. What are we accumulating? Areas of little rectangles, or skinny rectangles, right? So I want you to think how this works. If I were to illustrate some of these rectangles with some representative rectangles, they could look like this. There'd be some over here. I'm doing a left sum for some reason. Doesn't have to be that, but here's some of the rectangles there. As I accumulate those rectangles, let's think about the dimensions on those rectangles. The base length is right here. How would you guys describe that base length of the rectangles? Did you say n? So n would be like the number of rectangles if we think about those Riemann sums.
1 over infinity.
So yeah, 3 divided by n, right? So and n would depend on the number of rectangles. But don't we know we're headed towards an integral?
Yeah.
Like we're headed towards an integral here because we want to find the exact area. And so 3 over n is definitely the width of the n rectangles over the interval of 3. But isn't the integral going to take the number of rectangles and make the number of rectangles approach infinity?
Yeah.
What's that going to do to the width of each rectangle?
Really small.
Really small, heading towards 0. And so it's like infinitesimally small. It's like this little itty bitty width or base length. What do we call that?
A limit.
Well, the limit is what's making that happen. But the way we note it, this is really good. I'm glad we're talking about this. We would say that base length that's getting like skinnier and skinnier, closer and closer to 0, we would actually call that dx. That's a little tiny change in x. Like a little itty bitty change in x. Did you say that? No, okay. I'm sorry if I sometimes I don't hear. Yeah, so it's a little tiny change in x. And what is the height? It's the y value, isn't it? So the area of any one of those rectangles is y times dx. So you could say, all right, I'm going to be adding up a bunch of these. Technically, it's y times dx, height times base. But I don't think we'd ever write that because we know what y equals, don't we? So instead of writing y dx, I would write x over x squared plus 1 dx. All that really is y times dx, a height times a base for those representative rectangles. Okay. Did anybody take this any further? Take it all the way through to the end?
Yes.
Does this end up being natural log?
Yes.
It does. Here's how I would do this. I would ask myself, what is the derivative of the denominator? 2x. Doesn't that mean that Timmy messed up by a factor of 2? So I'm just going to go times 2 in the top, and then I'm going to balance that out by putting a times 1/2 on the outside. Just like we've done before, that's just really multiplying by a smart 1. I've set this up perfectly for a natural log chain rule. So the 1/2 does not go anywhere. The ln is what results. So ln of x squared plus 1. And here for the first time is where the absolute values might matter. They don't, but they could matter depending on the interval that we're using, because we're going to evaluate from 0 to 3. If that 0 or 3 caused a negative, then we're going to have an issue with ln. They don't, but it could. Okay, so FTC1 tells us to do 1/2 ln of 9 plus 1, which is 10, minus 1/2 ln of 0 plus 1, which is 1. Oh, I'm sorry, did I mess up?
I'm just wondering where the C went.
Oh, so it's a definite integral, and so we typically don't write the C. We could, though. So the general principle is if you have your limits of integration, then we don't write the C. It's not that there's not a C, it's just that the C would subtract out. Let me show you where that comes from. So if I did put a C in there, it would be plus C, and it would be evaluated from 0 to 3. So when I do FTC1, it'll be C minus C. So we'd have 1/2 natural log of 10 plus C minus 1/2 natural log of 1 plus C. So the C's would add out. Let me finish this out real quick. What's ln of 1? 0. And 1/2 times 0 is 0. So we could really just write this for an answer. 1/2 natural log of 10. You could actually even manipulate that a little bit too. So, Jake, go ahead.
Can you show us how you would do this with the substitution?
Sure.
Would the 3 and 0 change? That's what, because remember when we said like.
Oh, if we're doing U sub? Yeah, for sure. Lainey, your question?
Well, that would,
So would it,
plug.
If we're going to do U sub,
because this is what I got.
can I do that?
Yeah.
It should be 1/2 ln of 10.
But what did you?
I want a 101, because I got it from 10 to 1, because I plugged that 3 into the U. My
Oh,
U was
can I do it real quick?
Yeah.
Let's look. Okay, let me erase a bunch of stuff here. We'll do U sub. Okay, so for Jake, Ben, Laney, others perhaps, U substitution, what I would do here is I would say U equals the denominator, and therefore du is equal to 2x dx. So I'd come over here and I'd write integral of something over u. I've got the x right there. Dx would get replaced by du over 2x. X's cancel. So far so good, right? As far as the limits go, we're going from 0 to, oh, I know what you did. I'm glad you did what you did. The limits are going from 0 to 3 with x's, so I got to convert those over to u's. So I plug in the 0. 0 squared plus 1 is 1. 3 squared is 9 plus 1 is 10. So we agree on this, right? Laney, we're good? Jake, we good? Okay. So now I can do my ln. So the over 2 is really just a 1/2 out front, isn't it? So I'd get 1/2 natural log absolute value of u. Here's where you went wrong. I know for sure Ben did this. Ben took the x squared plus 1 and plugged it back in. And since you converted everything over to u's, you don't want to do that.
Yeah, and then I got 10 squared plus 1.
Right, you leave it as u. Like if you convert your limits to u's, if you convert everything to u's, including the limits, you leave it in terms of u. You don't plug the x squared plus 1 back in.
So then would it just be U?
Yeah, so it'd be ln of u, 1/2 ln of u, evaluated from 0, or not, sorry, from 1 to 10.
Well, then what is you?
Right.
Oh,
So this would give you 1/2 ln of 10 minus 1/2 ln of 1. So in this original, it's x, 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 and x. And a second ago you said, what is u? They're all u's now, because what we did is we converted everything to u's. So now it's u, 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 and u. So the 1 and the 10 are in terms of u. And so when it comes time to plug those in, you plug those in for u.
So that'd be the most simplified then? Or like, would you take that answer?
I would take that answer for sure. ln of 1 is 0, so you could just write 1/2 ln of 10. But I would take that answer too. That's fine. Okay, Jake, did I clear anything up for you?
Yeah, that makes sense. Thank you.
Did you do the plug back in thing?
Yeah.
Okay, so hey guys, let me clarify. I think we can be very formulaic here. If you're doing Ben, very formulaic here. If you're doing a definite integral, don't plug back in. Like, don't substitute back in. If you're doing an indefinite integral or just the antiderivative, yes, you do. So I think that would be a good rule of thumb. Really awesome questions. Anybody else? Anybody else? Okay. Fair enough. Does anybody, we got like 5-6 minutes here. Oh, I'm so sorry. Go. Question.
This is going to calculate acronym test, this part.
Number 8?
Yeah.
No way, Jose.
What? Rick mean.
So, but let me clarify a little bit for you. So Jackson, like it literally, if we took number 8 and we said, okay, number 8 is going to be on a quiz or test, would I change anything about it? I would change one thing about it. I would give you the graph.
So then,
How do we calculate?
You don't. You don't calculate anything. You just say the answer is 1/2 ln of 10.
where did the 10 come
Just
Sorry,
x
my bad.
squared plus 1.
Well, did you use substitution or did you use Timmy messed up the chain rule?
That is an excellent question.
Because where it came from kind of depends on
I
that.
mean, I got up to that step where it's like 1/2 ln of x plus 1 plus c, and I was like, that looks good. But I don't know where, I'm from 0 to 3. But, yeah.
Did you end up with
X squared, 3 squared plus 1, 10, 0 to 10, is that?
Okay. So you're okay with this part, 1/2 natural log, absolute value of x squared plus 1?
Yeah, I totally got it.
So you're okay with that?
from 0 to 3?
Am I right?
Yeah,
And are you okay with the from 0 to 3 part?
yeah, that's what I got.
So this is definitely connecting back to chapter 4 with definite integrals. If you are evaluating a definite integral, like in this case from 0 to 3, what you do is you plug the 3 in for x, and you plug the 0 in for x, and then you subtract those two evaluations. So it'd be 1/2 natural log of 3 squared plus 1. So that's plugging in that 3 minus 1/2 natural log of 0 squared plus 1. That's plugging in the 0. And you subtract those two, you find their difference.
And that's just 0 on the second one. So
And yeah, so yeah, ln of 1 is just 0. E to what power is 1?
Would we just have to like know that? Just memorize it?
So how are you supposed to know that? So it was in Algebra 2, it was in pre-calc. We actually quizzed on that, the very first quiz this year. ln of E, ln of 1, ln of 0.
I got all of those wrong.
So Jackson, you have options.
Is there a way to derive it, like if I forget that?